So welcome to the second part of the talk on Python design patterns. Just as a reminder, like in part one, we're mostly talking about a lower to middle level of mastery of design patterns themselves in a middling to good level of mastery of Python. This talk in particular, the second part, will cover behavioral patterns. So it's about 35 slides and going over essentially template, state, and strategy, which means we have to skip all the first part because it's a single presentation. Thanks for your patience. More close. Okay. So as this short summary may have reminded you, in the first part we went not in too much depth, more in breadth, over a lot of structural and creational patterns. In this part, we will drill more in depth in just a few behavioral patterns. Most patterns are behavioral, that is, they have to do with the way objects behave. And of course, we would always want to have good behavior when possible. So we're going to be talking about template method, which I prefer to call self-delegation, which is the heart or the essence of object-oriented programming. And then we'll take a slightly original view at state and strategy as factored out version of template method, as we'll see. So as I mentioned earlier, template method is a great pattern with a lousy name because template means very different things to different people. And a better name is self-delegation because it's directly descriptive. The classic template method situation is an abstract class, abstract base class, that offers an organizing method. That organizing method calls what we denominate hook methods. In the abstract base class, hook methods remain abstract. In the concrete subclasses, all the hook methods are implemented. Client code calls the organizing method typically through a reference to the abstract base class, which in practice indicates, of course, a concrete subclass. So this would be the skeleton. We have some organizing method, which in this particular abstract base class is rather silly, just calls the two hooks method one after the other. Do this and then do that. But then the job of the concrete subclass is to instantiate do this and do that to actually do whatever is appropriate for this case. And the client would call org method and get the two steps, the two concrete steps. Let's give a slightly more fleshed out example. Suppose we want to abstract the general task of paginating some text. Some text, meaning a sequence of lines, needs to be presented in chunks, which we call pages. And the task has to do with remembering how many lines are supposed to make up each page, output the lines one after the other, tracking how many we have placed on the current page, emit a page header just before each page and a page footer just after each page. This is sufficiently generic, but sufficiently substantial that there is actually some work to do. We can factor out the structure that we just presented in words into actual executable code in an abstract pager. So the abstract pager has to know about a maximum number of lines per page, MX, so it will have to get it in the initialization init method and record it as a class instance variable. And it also will need to track how many pages it has emitted so far and what's the current line number. So it will start at 0 variables named self-cur and self-pg. And then the organizing method is the one that emits a line, writes a line, given a line of text, presumably. If we are at the very beginning of a page, so the current line within the page is 0, first of all, there will be the header. The header, we assume, can take the page number as an argument, so it may print a page number or something. Then we'll write the line, increment the current number of the line on the page. If we've reached or exceeded, should never happen, but who knows, the maximum number, then we'll do the footer, again passing the page number in case the footer method wants to print the page number instead. And then we'll reset the current number of line on the page to 0, and the page number will increment. So basically, this doesn't tell us anything about what does it mean to do a header. What does it mean to do the actual right of the line? What does it mean to do the actual footer? But it abstracts everything else. All of the organization, all of the logic about keeping the pagination together goes in this method, and none of the concrete details about header, single lines, and footers. So once we have this abstract pager, we can subclass it to make concrete pages. For example, this is a pager that goes to standard output, presumably to be piped into some kind of printer. In this case, since we're dealing with standard output, doing the right of a line is just a print of it. Doing a header, maybe page number something and a couple of white lines, and the footer may be a form feed. Of course, this is like kind of arbitrary, but this would give you somewhat reasonably paginated text if you piped it to a line printer that does the right thing when it gets a form feed, that is, goes to the next page. And this is a completely different implementation that uses curses. I assume we have the normal Python curses, but it's very similar if you only know the C version, it's very similar, to paginate text on screen, kind of like more, of course, without all the fancy stuff. In this case, we start with a different default maximum, 24, because that's the traditional depth of a terminal, and we make sure it gets recorded properly by calling the initialization of our superclass. We also need to record the window, in curses terms, the window object on which we're actually doing the output. So now in this case, the emitting of a line is the add_str method of the window with a line number and x offset. A header means going to the top left corner and clearing the page. And the footer in this case is actually waiting for a key press by a getCH. This is apparently different semantics. We're not emitting any decoration for headers and footers, but it basically shows how the concept of pagination generalizes to one screen after the other, posing for a keystroke at the end of each, no matter how different the task may look from just getting onto a printer. So why do we want to do that? Because all of the structural logic goes into the organizational method, and all the actual elementary actions, the concrete stuff, goes in the hook methods implemented by the concrete subclasses. And this separation of concerns is very often appropriate. The abstract logic that organizes the sequence of action goes in one place, where it can then be reused by a very different set of actual concrete actions. So this is a great way to focus on the responsibilities and collaborations of the different classes, and therefore of the objects of those classes. The base class job is to call the hooks. The concrete class jobs is to supply them. And this is the template method concept is also behind the typical framework approach of object-oriented programming. It's not the code that I write that calls functions from a library, as much as it's code provided by the framework that calls specific concrete methods in my own objects. There's a choice about what to do in the base class regarding hook methods. So the traditional approach would be the second one here. Force the subclass to implement that particular. And the way to do that in Python is to raise not implemented error. That means that if this isn't overridden and gets called, then the program terminates with a not implemented error, which is a pretty clear indication of what was wrong. Or you could simply avoid writing that at all, in which case you'd die with an attribute error, which isn't quite as precise, but it's much handier. On the other hand, it's often the case that hook methods are provided, but in many concrete subclasses, they won't really need to do anything. So the body of pass, meaning do nothing, is going to be in most of the concrete subclasses you actually write. In this case, it's much more practical to actually provide a no operation default, a default of whatever is needed most often, but that's very often a no operation that is a pass in Python terms. And then subclasses that don't actually care about this particular hook don't need to do anything, which, particularly if you have many subclasses, is extremely handy. The only real reason to do this in some cases is that they're good documentation. Instead of having to pick up what are the hook methods by deducing their hooks from the no operation implementation, you get it pretty strongly. I will admit of a strong bias toward practicality in this case. The reasonable default hooks are so much more often appropriate in Python. Another thing that Python offers that most other object-oriented languages don't, in most object-oriented languages, you can only override code, methods. In Python, you can also override data. And sometimes that's much handier because it completely does obviate the need for boilerplate accessor, get this, get that, get the other. You simply access, say, self.mx and record mx at class level, and the one in the subclass overrides the one in the superclass for instances of that subclass. That's very practical. OK, here's a more challenging example from real life. You remember my general stance. Patterns are not invented, they're discovered. You abstract what is in common between a lot of independently developed real cases. So known uses for a pattern are an absolutely crucial part of the presentation of that pattern. And I have picked some of the known uses of template method from the Python standard library. So the Q method containing the Q class, so q.q, is essentially at the heart of Python multi-threaded programming. It's a thread-safe, first in, first out queue, and the typical architecture of a Python multi-threaded program that's well written is some threads generate units of work and put them on queues. Other worker threads peel unit of work off the work queue and generate results and push them back onto results queues. Any other structure means 90%, 99%, the author of the program hasn't really understood threading in Python. You can do in other ways, but this is so often appropriate. So it should be one of the most widely used classes if you're good Python programmers and need to do multi-threaded codes. What makes it so good, besides its eminent practicality, is a very nice, very clean separation of concern, which boils down to a template method, design pattern, between what does it mean to make the putting of one item onto the queue thread safe versus what does it mean to actually do the putting in question. So the public method put is essentially concerned with acquiring a lock, waiting on that lock if needed. That's because you may declare a maximum dimension of the queue, so every thread trying to put stuff on an already full queue will wait until some worker thread peels things off. Then once you're really in the right spot where you're fully thread safe and everything, called underline put, the private version of the method, and then notifying the condition not empty, because similarly, anybody who's trying to pull item from a queue that's empty is going to be in a wait state on self not empty. And guaranteeing, of course, the release no matter what, even in cases of exception and so on, by a typical try-finally construct. Underline put, if you look at it, is trivial. It does self-queue append. Self-queue being a double-ended queue. But the interesting point here is that all the delicate, error-prone, hard-to-test stuff having to do with making things fully thread-safe is abstracted in the organizing method, and the hook method is the one that does the simple job in a fully, it doesn't have to worry about threading at all. Queue is not an abstract class. 90+% of the uses will be as a concrete class. Particularly because it does first in, first out, which is what you most normally want from a queue of task or queue of results. So maybe in one case in 10, do you actually need to do anything more sophisticated? Since it's not abstract, it fully implements all of the hook methods. That is not a violation of any sacred principle of the template method design pattern, just a very practical choice. The subclasses, if you want to write subclasses, will be for the purpose of changing the queuing discipline. You may want a priority queue, a last in, first out queue, or any sort of fancy stuff, and you will not have to worry about locking and race conditions and so on. You can choose to override the hook methods in a subclass. There's a few in it, which does whatever initialization you need. Queue size, return how many items are in the queue? Is the queue empty? Is the queue full? Put one item, get one item. And there's a Python special. You can also override the data. I already mentioned that, but here's an example. The simplest example, suppose we want to use a thread-safe last in, first out queue. There's two perfectly valid approaches. One of them is, well, we have a double-ended queue. We may use it as a last in, first out instead of first in, first out. Simply when we put, instead of append, which goes to the right, we use append left, which goes to the left. So things get appended and taken off from the same extremity. You might notice that a double-ended queue is always a slightly heavier data structure than a list. A list doesn't offer O1 access at both ends, but on the other hand, as long as you only need to add and remove stuff from one end, it's still O1, but it's much faster. So if you have, if you are going to have a lot of data and a lot of activity in your LIFO queue, you may want to implement it by, in the initialization, make self-queue a list instead of a double-ended queue. And then the pop, which does the append, can keep working like that, and the get simply needs to do the pop. So this is a bit more code, but you're using a normal list instead of a double-ended queue, so probably each get and put, apart from the threading override, of course, if any, can be easily twice as fast. So it may be worth it in some cases. Here's another known use of template method, which is much more typical. It's the CMD module of the standard library. So CMD basically organizes a console session of commands. You have to define the commands. And the key organizing method is called CMD loop, and it encapsulates all the structure of, let's do a session of interactive commands. So self-pre-loop, the default hook implementation, is a pass. Is there something you need to do to prepare before the interactive loop starts? And then forever, until further notice, do input. The default is read input from the terminal. Pre-command, pre-process the command, break it into whatever kind of things you need. The default does nothing. Do command, we'll actually go to that later, that is, actually obey the command. Do some post-processing based on the flag returned by do command to see if the whole session is over. If the result of that is actually true, then break. And then post-loop, which again, by default, is nothing. So basically, this is oversimplified. There's actually, if you actually look at the sources of the CMD module, there's prompting, there's automatic help for commands you supply, and so on. But this is the essence. It's a series of concrete things, most of which can very well be no operations, like the pre-processing and post-processing in most cases, or the pre-looping and post-looping. What you need to do is essentially supply the actual concrete step, and then you can launch an interactive session of commands. Another typical example, AsyncCore is a pretty old component in the Python standard library, which does asynchronous network programming. And it's most of the methods you end up calling on AsyncCore objects are organizing methods. For example, somebody calls a write that goes to handle write event, which is an organizing method supplied, which first of all says, okay, are we connected? Well, oh, sorry, this is a C, not an X, it's handle connect. If we're not yet connected, then handle the connection and remember it for the future, and then do the actual write. So basically, if you want to be able to write to a socket that isn't yet connected, or you don't have to worry about how to do that. You can just accept the organizing method, and you have to basically only write this loop to actually to this hook method to actually do the writing when the socket is connected. Don't have to worry about buffering or anything. An interesting variant of template method is the mixing class. So it's not presented that way in the classical Gang of Four book, and it's probably very alien to most people who do object-oriented programming today, because they use languages that don't supply multiple inheritance, and so mixing class just can't exist. But for people with background in object-oriented programming in Lisp, for example, or C++ for that matter, it should be pretty familiar. So the concept of a mixing class is essentially the class-level equivalent of what template method is at object level. A mixin is an abstract class which is meant to be multiply inherited from. It supplies organizing methods only, so to speak. It does not supply the hook methods. It's the job of the concrete classes which pull together various mixins to actually fix the hook methods. And my example from the Python standard library of a very useful mixin is dict mixin. So a dict map, if you want, is a very rich interface in Python. You can do all sorts of things, which is great when you're using a dictionary, but when you're trying to implement a mapping, there can be a lot of code you have to write, which is kind of repetitive. Well, you don't have to, because you can multiply inherit from dict mixin, and you only have to supply a few hook methods. At the very least, getItem, the special method which lets your objects be indexed, and keys to return all the valid keys in your mapping. And if you read-write, also the methods to set and delete items from your mapping. Normally, you will have some work to do in initialization and copying, and that's it. Everything else has semantics defined in terms of these elementary methods, everything else in the huge dictionary interface, and so you don't have to supply it. You may supply it. For example, the default implementation of under contains under for membership checking is, okay, generate all the keys and one by one check if is it equal to this, it is equal to that, is it equal to the other. So basically, you're default implementation of contains is order n, while depending on how your mapping is actually implemented, it's typical to be able to do it in O1 or O log n, so you should override contains for performance reason. But performance is one issue. The point is, in terms of functionality, you only need a handful of methods, and everything else has semantics defined in terms of it by the code in mixin. So, for example, this is the equivalent of contains, is has key. So this is very obsolete, but it's still supported for backward compatibility. This is the real thing, but it's basically the same semantics. So the way dict mixin implements this is it tries indexing the object itself, and this implicitly called getItem. So this is a self-delegation, although it's not immediately obvious. And if the attempt to index fails, because the index isn't there, key error, then husky is false, otherwise husky is true. So this is O1, but it can have heavy overhead because of the expected exception. When an exception actually happens, it costs a substantial amount of time. So you may still want to override this if your mapping affords a very fast way to check. How do you use dict mixin? Here is an example, a read-only mapping that takes a list of mappings, and when you try to get and index the chain, it tries in sequence indexing each mapping in the chain. So this would typically be the case, for example, for nested lexical blocks. You are in a nested chain of blocks, and you're looking for a name foo. Well, you have to look first in the innermost, and then one out, and then one out, and then one out, and so on. So a typical case of chains. Although in that case, you would also want method to add one to the chain, remove the last from the chain, which I haven't shown here. So it's read-only because it only deals with looking things up. So it only needs to record the sequence of mappings. When you try to get an item, it will, in sequence, try every mapping in the sequence, trying to return the key lookup in it, ignoring key errors. If it gets to the end of the loop, means the thing is nowhere to be seen, and therefore it raises a key error itself. And to get all keys, I'm using set because it's easy to accumulate it, but in the end I have to turn it into a list because that's what keys must return, a list of keys. Okay, so this is template method with essentially a classic approach and very minor Python-related variation. But let's move one step further. Is this organization always appropriate to have the self-delegation in the strict sense, the organizing method in the base class and the hook methods in subclasses of it? Subclassing has advantages, but we already mentioned there are some issues with it as well. Why can't we have the organizing method in one class and the hook methods in another? The answer is we can perfectly well. And although this pattern might be worth another name, I'm still considering it a Pythonic case of template method. So for example, in HTML, the formatter is essentially the organizing class. It does hook calls not onto itself, but into the writer instance that it's passed. So to make a concrete writer, you essentially implement only the hook methods, but then but you don't have to subclass from formatter. You can implement it in any way you wish. So you still get essentially all the advantages of template method without the subclassing. An example which could be more familiar to people familiar with other languages is SAX, the simple approach to simple asynchronous XML parsing. There, a parser object essentially calls hook method on a handler object. And the concrete handler object needs to implement the method, but the organizing methods come from parser. Essentially, this adds one axis of variability and therefore flexibility, and is starting to shade toward the strategy design pattern, as we'll see later. Essentially, in strategy, you want to have one abstract class per each decision point you have in some algorithm or complex of algorithms. And then concrete classes at each decision point, which subclass the appropriate abstract class, and are otherwise independent from each other. And that's fine when what you do at the different decision points is kind of totally decoupled. But sometimes you don't want that. You want bunches of decisions to be made. For example, you don't want a writer, the decision of what do I do when I write a non-space character versus what do I do when I write a space character. They're not, it's not appropriate to totally uncouple them. What is now? Sorry, this was interesting. Okay. You group the decision point into one thing because you don't want complete orthogonality and independence of what is the concrete step to. I'm sorry, I have no clue what is going on here. Something taking over my machine. Okay. So, Python offers strong introspection, and template method works very well with introspection. The organizing class, whether it's an abstract base class or a separate one, can snoop into the class that supplies the hook, which could be a descendant or could be a separate one, as I already mentioned. At runtime, find out which hooks are actually supplied and behave accordingly. Dispatch things, including catch-all, error handling, whatever, depending on what hooks are actually being supplied. So I did mention CMD earlier. Well, here is what it means to do one command, the do CMD hook. This is the default implementation of do CMD hook. It basically checks, OK, so this is a CMD, and its argument, it's been parsed. Say CMD is foo, string foo. Well, does self have an attribute do underscore foo? Well, then we call it. Otherwise, we move to the other hook method known as do default. So basically, by simply writing do this, do underscore this is the mandated naming convention, do underscore that, do underscore the other, you're supplying hook method for commands this, that, the other. Another variant. You may have multiple kind of template methods. The plain kind or classic kind, the one factored into separate classes, which I've mentioned, and the introspective one. So those multiple axes, they allow you to separate very carefully variabilities that are distinct from each other. I consider this an advanced subject in that trying to follow three harmonies at the same time, unless you're really into Baroque music, can be pretty hard. On the other hand, all art aspires to the condition of music, and this must include the art of programming. Incidentally, finding out who said all art aspires to the condition of music beat me. I found Pater, Pound, and Santayana all widely credited with the same wonderful quote. This is the unit test module in the standard Python library, a simplified version of what it means to call a unit test. It interleaves the introspective, classic, and factored out kind of template method. So to find out what method should I call, it does a get after on self of a dynamically constructed string, and then later it calls it within a try clause. So this are pieces of a introspective template method implementation. In the organizing terms, executing one method in a unit test means doing the setup, doing the method, doing the tear down. This is the simplest kind, traditional template method design pattern. And each is done in a try except because all of the exceptions must be diagnosed in a carefully controlled way and not just propagate and terminate the test. And then finally, when there are errors or successes, they go onto the separate object result, which is essentially the implementation of that. Essentially, instead of having the test case itself have the concept of accumulation, it's separated into the test result abstract class. So this is our fuga tre soggetti. So I did already mention that state and strategy have some similarities to factored out template method. So it's factored out, meaning the organizing method is in one class and the hooks are in another class. So the organizing method doesn't call self.doHook, it calls self.someDelegate.doHook. This is why it's factored out. So in the classic vision, the strategy is one abstract class per decision point. The object behavior is factored out to the strategy concrete classes, while state would be the fully encapsulated and strongly coupled variant of that. Python further complicates the distinction because if you want, you can switch out dynamically the class of the object. You can change the class of the object as you go. Which isn't exactly the cleanest way to proceed, but it does work. And you can do the same for a single method or two, which is more likely to make sense. So here's an example of strategy. I'm trying to boil things down to the simplest case where I can actually give an example of both approaches. So we have a calculator, and our decision point, I've carefully chosen one only, is how do we show results? So we do computations, and then what do we do with the results? How do we show them? So the self.strat is the strategy reference, and it starts with a show class, which presumably does the showing. After each computation, self.strat.show gets a nice string, which it shows if it wants to, because the decision of whether to show or not depends on our strategy class. And to change strategy, we have a setVerbosity method on the calculator itself, which, depending on a flag, whether to be quiet or not, sets strategy objects in class show or class quiet, presumably, as the name indicates. Class quiet just has a no operation show method, so there is no output while verbosity is false, and the other one does some showing. This is how you could implement them kind of trivially. In the show case, the show actually does a print. In the quiet case, the show does nothing. So how would an implementation of the state design pattern for exactly the same purpose differ? Well, we would have to presumably call the thing self-state instead of self-strat. But basically, it would be all the same, except the verbosity, the setting of the verbosity, that is the state transition in this framing of the problem, would have to be also delegated to the state itself. So the state itself should know what to set its own verbosity means, depending on whether it's being asked to be quiet. I have had to look for kind of stretched out examples of strategy and state to show how, are these really two different patterns? Because I don't think they are. But their normal range of application isn't quite that close, as I've shown here. And this would be the state classes. Basically, I've chosen to implement them with inheritance simple because this way I could fit them on the screen. But essentially, the set verbosity is right here. As you see, it's very closely coupled. I've added the close coupling only because it's a traditional feature of the state design pattern. Essentially, the state design pattern in this case changes the state of its context in this way. This is an example of state class, which can be implemented in a particularly different way in Python. Consider a ring buffer. It's essentially a first-in, first-out class with a finite memory. You only want to store the up to max items, no more. For example, you want to keep track of the last 100 log lines, but when you have more, then the older ones need to be overwritten. So it got two macro state intrinsically. Early state, you don't have max items yet, then new items as they come in just get appended. Late state, then the new items are overwriting old ones. And the switch from the early to the late macro state is massive and irreversible. You never need, in this simplified case, to go back. And it's massive because the details of the behavior are totally different. So this is a good example of switching class. There aren't all that many, but this is one. It's basically we're switching implementation class, if you will. At the beginning, self-D is a list. And transforming ourselves into a list just means making a copy. And appending just means appending to the list. But if we've reached the maximum, then we need to change our class to the different implementation class, which is a full buffer. Of course, you could do this in other languages with like one more level of indirection by switching the class of the implementation and having the envelope stable. And this is how a full buffer behaves. Appending means overwriting a certain item and incrementing the index of the next item to be overwritten. And to get back into a list needs some slicing and splicing. Nothing really complicated. Or another Pythonic alternative, you could do it by just switching a method. Note the similarity to the previous case. The only issue is when the normal append notices the length has reached the max, then it switches its own implementation to append full, the implementation of the method without needing to change the whole class. And this is append full, which I've implemented in a simpler way this time because I just didn't have time on the slide to put in all the code. This also allows us to keep two lists the same. But this isn't very fast. This is ON, which doesn't make really sense. OK. And this concludes the second part and second and last part of our Python design patterns. Questions and answers are welcome. Thank you. Catch up on the delay. I may have kind of rushed over some point or other, so anything unclear? Well then, thank you very much.